So this only operator can be self-adjoint, right?
Yeah, you don't say functions are self-adjoint. That's yeah. Okay, so let's accept the following fact so far. I didn't prove it in more generality, but it's like this. If you define a weighted inner product as integral from a to b of f of x times gx bar. Bar doesn't mean anything if it's a real valued function. Times wx dx. And you can check, it's almost the same proof. You can just review what I did for the case when wx is 1, and it's exactly the same proof. Okay? And for this wave function, the L operator, which is, what is that? Negative 1 over wx d dx p of x d dx of this thing here, plus q of x of this thing. So if you plug in f here, then it means that f is here and there. Yeah. So this entire thing with negative 1 over wx. Under this inner product, you can show that L of f of x, g of x, is equal to f of x, L of g of x. Okay. So L can be moved from one side to the other, then that's called self-adjoint. So in other words, L is self-adjoint. Now I'm ready to explain this other phenomena of orthogonality. So you've witnessed many times when we are trying to solve PDEs by separation of variables, we end up with the Sturm Liouville problem, and somehow all these vectors were orthogonal to each other for different eigenvalues, right? There's an easy explanation why that is so. So let's say L of f is lambda f, and L of g is mu g. So in other words, f is an eigenvector with eigenvalue lambda, and g is an eigenvector with eigenvalue mu. Okay? Yeah. And we also know that since L is self-adjoint, lambda and mu are real values. Okay? So those were the things that we've already talked about. Then, here's what I want to show you in general. If lambda and mu are different, then f and g are orthogonal. So in other words, if you multiply them, you integrate from those two intervals with the given wave function on the right, then you get 0. That's what you get. Yeah, so I wrote it very cryptic, but you've seen it before. That all kinds of integrals give you 0, and all you need is this self-adjointness. Okay. So let's show you the proof. So proof, we use the fact that L is self-adjoint. So what we do is we evaluate LFG in two different ways. What's LFG? That's lambda FG. So it's lambda times FG. Right. What is FLG? Sorry. Self-adjoint. Because L is self-adjoint, you can move this L to the other side, so these two are the same. But what's L of G?
mu g.
Mu g. And although the Hermitian product is sesquilinear, so that you have to bring this out as a mu bar.
Mu bar.
Mu bar is same as mu, right? Because it's real. So you get mu fg. So we have the identity that lambda fg equals to mu fg. So we move this to the other side, we get lambda minus mu fg equal to 0.
Either the first or second term or 0.
Either this is 0 or that's 0, but we have lambda and mu different, right? So you can divide this away and you can make the conclusion it has to be 0. So here's a very important thing that we just discovered. As long as you have self-adjointness, you have real eigenvalues, right? And you also have orthogonality between eigenfunctions of different eigenvalues. Now, what's going to be more important is,
so the prerequisite represent is all the self-adjoint operator, right?
what's that?
So any self-adjoint operator has a property.
Right. So
not only
so this
L.
this is true in finite vector spaces. Okay, if you have any self-adjoint matrix, then you can collect all of its eigenvectors, and these eigenvectors form the basis for the entire vector space.
Yeah.
And they're real eigenvalues, right? Using that basis, if you represent the matrix under that basis, the self-adjoint matrix becomes a diagonal matrix with real entries. Let's see. Yeah, diagonal matrix with real entries, right? And because it forms a basis, any other vector in that vector space can be represented as a linear combination of these eigenvectors. So, here's the idea. The idea is that if you have a self-adjoint operator, then find all its eigenvectors. It will give you a basis that you can conveniently express every other function as linear combination of that. Now, when it comes to infinite vector spaces like function spaces, that becomes harder. That actually requires a very hard amount of work. So what I did show you is that the eigenvectors, if you collect all of them, they give you a complete set of bases. That's harder to prove. Yeah, I can't prove it.
Infinite.
You have infinitely many of them, but any other vector that would be like linear combinations of these. So if it's L2 and it satisfies these two conditions, we don't care about this one. If it just satisfies these two, then that can be represented as an infinite series of these eigenvectors. That's called completeness. You're not missing anything. If you have a basis of vector space and you take one vector out, it's no longer complete, and that means there will be vectors where you cannot represent by the set that you have. But if you have complete space, a complete list of bases, then any other vector can be represented as a linear combination. And that was very crucial when we solved the PDEs. Okay. So that part is something that I'm not showing you.